Hello and welcome to Naughty Daddy's Guide to Computing, from Maths to Minecraft. In this video we're going to look at a NOR gate. In this case I've taken the liberty of already drawing the circuit so you don't have to waste time with me fiddling around trying to draw it neat. Not that this is terribly neat anyway. I'll just quickly guide you through. This is the actual symbol for a battery. And the plus side is up here. I've labelled this plus 5 volts, but it's just whatever the voltage of your battery is. So your higher current is coming through here, and this is where the wires join back to the lower part of the battery. So there's 5 volts potential difference between here and here. So that's your positive end of the battery, that's your negative end of the battery. Okay, so this is our output of the entire circuit. This triangle with the arrows coming off is a light emitting diode, or LED. Without the arrows, this is just a regular diode. A diode allows a current to travel in one direction and one direction only. With these arrows, it basically lights up when a current does flow through it. This is the symbol for a resistor, so its job is to make it harder for a current to travel through. If you want, you could imagine these as nice lovely straight roads that cars can travel on, and this is a narrow cobbled road that's very uncomfortable, and drivers prefer not to go down this road, and they will only go down this road if all the other routes are blocked. That's because electricity likes to take the path of least resistance. Okay, so here we have 3 transistors. First transistor, what we have is a current going into it from A, which is our input, and we have a current going in from this one, B, which is our input. That current will either be present or absent. Now this transistor, there are 3 inputs here. The input here I believe is the base, and I believe these are the collectors and the emitter. Collector and emitter. But the whole point of it, if a current goes through here, then a current is allowed to travel down here. If there's no current coming in here, no current is allowed to travel down here. So this is from our inputs. These could be attached to a manual switch which is connected up here if you wanted to manually input, or it could come from another circuit if we wanted to. This part of the circuit here is our OR gate, and here we have the output from this OR gate I've labelled A or B is going into our NOT gate. So let's explain the OR gate first of all. Because these transistors are connected in parallel, if a current goes into A, then a current can come down here, through here, and into our NOT gate. On the other hand, if B has a current going in here, then this opens this path for the current, which can travel down here and through here and into our NOT gate. Again, if both of them are on, the current will be split 50-50 between the two, rejoin down here and come back through here into the NOT gate. So only if both A and B are in the off position, only if there's no current in A, no current in B, then we will have no current coming here. Current present corresponds to binary 1. Current not present corresponds to binary 0. Okay, so here we have our NOT gate. So only if there is a current coming through here will this transistor allow current to pass through it and down here. This will then bypass this whole part of the circuit. If there is no current coming through here, that is to say if both A and B are off, then there's no current coming through here, this transistor is not allowing current down, then the current has to go through the resistor to turn on the LED and give an output here. So if there is no current in here, no current in here, there will be a current coming out here. So in other words, if that is 0, if A is 0, if B is 0, the output will be 1. If there is a 1 in A or a 1 in B, the output will be 0. Again, if both A and B are 1, the output will be 0, which is the logical NOR gate. If we want to change this NOR gate to a NAND gate, all we have to do is connect these transistors in series instead of in parallel. So I'll grab this transistor here, I'll pull this down here, connect it to this transistor, which means we no longer need any of this. So that can all go. And all I need to do is connect this transistor here. And there we have a NAND gate. In this case, only if there is a current going in here and a current going in here will the current be able to travel down here. If there's no current here, the current is stopped here, and therefore it has to come down here and put an on. If there is, if this one has a current going in and this one has a current going in, then and only then can the current go through both of these and through this one, opening this one, allowing the current to come down here, and therefore there will be no current coming down here, so this output will be 0. So let's just go through all the combinations. If A is 1, then the current is blocked here because B is 0. If A is 0, the current is blocked here. If A and B are both 1, then the current comes through here. This is 1, and this should no longer be A or B. It is now A and B. So only if A and B, only if both of them are on, then the current comes down here, allows the current to go through here, which means this will no longer have any current, so this will be 0. So our truth table will then look like this: A, B, out, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0. Okay, and that's our NAND gate.